Hello, my name is Debra, and I would like to demonstrate my ability for you to have understanding after I have given you an explanation on a somewhat difficult problem. So you have asked to work this through. This is a solubility problem where you're going to have excess of a common ion, and that's what you are really concerned with in a problem like this, is if you have common ion left over. So you were given a volume and a molarity for the lead 2. You don't really care about the nitrate because it's going to be a spectator. Then you were given a volume and a molarity of I believe it was sodium fluoride. You don't care about the sodium because it is also a spectator. So what I've done is I've just written how you're going to get the quote unquote insoluble solid amount. So we multiply volume by molarity time for both components, both the lead 2 and the fluoride. And then what we need to know is which of those two is going to be limiting by applying stoichiometry. So because it takes twice as much fluoride as lead, then we are going to use all of the lead that is available, the lead 2 ion, and then we're going to use twice the amount of the available lead in fluoride. And sorry, that was my cat. He really wants to be part of this. So the leftover amount of fluoride is shown. It's the 0.0416. And also normally I use an external camera with a boom arm, and I don't have this kind of a glare on the whiteboard that I use. It's a real whiteboard. But for the demo purposes, the program kept asking me to expand my screen, so I was only able to accomplish that with the integrated camera in the computer. So we have leftover fluoride, and then for the solubility process, we're going to take the quote-unquote insoluble lead 2 fluoride, allow it to ionize or dissociate, and it really does not matter how much of the initial insoluble solid we have, because solids do not contribute to the expression for solubility. The SP means solubility product, and what product means is that you're only taking the product of the products, but you don't want to forget to raise them to their coefficients. So the expression then is going to be that you have KSP equal to the concentration of lead 2 times the concentration of fluoride squared, because the amount of fluoride is double that of the amount of lead 2 as it becomes available when the lead 2 fluoride dissociates. And we already know that we have extra fluoride in there. So not only are we going to have the 2x, which came from the dissolution of the lead 2 fluoride, but we're going to have the excess. So if you use the value for K that was given to you, the KSP value, which was 3.6 times 10 to the minus 8, and you algebraically rearrange this equation to solve for the amount of lead 2 ion, then you'll have this set up. You know the value of K. You know part of the value for the fluoride. It's expressed as 2x plus 0.0416 all squared, which means that depending on the way your instructor has suggested you're solving this, you may be using the quadratic equation because you have an x squared term and an x to the first power term. So you may be solving the quadratic equation. Otherwise, you could make the simplifying assumption that 2x is small compared to the leftover, the 0.0416, and you could make the assumption that this is negligible, that the 2x is negligible, and then you would just use the 0.0416 squared rather than also including the 2x term. And these are the kind of things that we used to do back in the day before cell phones. We would try it both ways and see how much of an effect that would have on our answer. But usually a general rule is if your K is 10 to the minus 5 or smaller, then it's okay to make the simplifying assumption that 2x is going to be negligible compared to, excuse me, the concentration that's already available from the excess fluoride. So you could solve it by just making that assumption and then just carry out this math here. And that will give you the value of X, which will be the concentration of lead 2 ion. Thank you for listening.